Hi, today we will be looking at section 4.2, which deals with introduction to permutations and factorial notation. So we'll look at a couple definitions and then we'll go into some examples. So for some definitions, permutations is arrangement of distinguishable objects. So let's say you have a family member that collects their figurines. The amount of permutations would be how many different ways they could be set up in a line. So permutations are an arrangement of distinguishable objects, and I should add in a definite order. Now, factorial notation is a concise representation of a product of consecutive natural numbers. So, for example, if we have 5 with an exclamation point, which the exclamation point is technically our factorial notation in mathematics, that means we start with 5 and then we continue multiplying by consecutively less values with integers. So we have 5 factorial is 5 times 4 times 3 times 2 times 1. And we always stop at 1. Okay, first example, a volleyball team of 7 players is taking a team photo. If they're in a line, how many permutations can they make? So if we think this through, we essentially have spots for 7 different players. So since we haven't chosen any players yet, for our options for a first person line, we'd have 7 players to choose from. Now that we've chosen one, we have 6 players left to choose from for the next position. And then we are going to have 5 left to choose from the next one. We've chosen 3, so that leaves us 4 left to choose. We've chosen 4, so that's going to leave us 3 left to choose. We've now chosen 5 players, so it leaves us 2, and then 1. So you can see that essentially, to answer this, we are going 7 times 6 times 5 times 4 times 3 times 2 times 1, which is just 7 factorial. Now we can calculate it by going in our calculator 7 times 6 times 5 times 4 times 3 times 2 times 1, which isn't too bad for this question, but some questions you might have values like 40 factorial. So you'll need to find your factorial button on your calculator. Now, if you have one of the Texas Instruments TI-80 283, to get your factorial, you're just pressing your math button, scrolling over till you reach the PRB menu, and then it's the 4th one down. So if we enter 7 factorial in our calculator, it gives us 5,040, which will get the same thing if we multiply 7 times 6 times 5 times 4 times 3 times 2 times 1. Now, in some cases, we'll deal with some algebra and factorial notation, and we want to essentially simplify these. So if we look at this, we have n plus 4 times n plus 3 factorial. N plus 3 factorial is the same as n plus 3. And then because we're multiplying by integers that are 1 less every time, if I subtract 1 from this, that gives us n plus 2. Subtract 1 from here, so n plus 1, or sorry, that should be times n plus 1. subtract 1 from that, that will give us n, subtract 1, that gives us n minus 1, and this will just continue on until we get a value of 1. So what we can see is this n plus 4 essentially extended our n plus 3 factorial, so this is just going to be n plus 4 factorial. Now, if we're doing division, we want to simplify. So typically I'll expand my factorial notation up top till I get what I have in my denominator. So we want to make sure in our numerator, we end up with an n plus 1. So we know n plus 3 would be our first term. If we subtract 1 from that, that's going to give us n plus 2. If I subtract 1, that's n plus 1. Now I could continue on, but because we're continuing on from here, I know that that's n plus 1 factorial. And that's over n plus 1 factorial. Now these essentially cancel out, so that gives us n plus 3 times n plus 2. Now we can FOIL this out because in some cases we won't want our answer as two binomial factors. So we've got n times n gives us n squared, n times 2 gives us 2n, 3 times n gives us 3n, and then 3 times 2 gives us 6. So that gives us n squared plus 5n plus 6 as our answer. Okay, so we've looked at simplifying. In some cases, we will have to solve for our n value. So for example, this first one, we have got 56 is equal to n factorial over n minus 2 factorial. So I'll start by rewriting it up here. So we've got 56 is equal to n factorial. We can expand that. We'll want to expand it just like with the previous example till we can cancel out this denominator. So that'd be n, subtract n from that, so it'd be n minus 1, subtract another 1, so that'll give us n minus 2. Now that matches what's in our denominator, so we'll put our factorial notation up. Then we've got n minus 2 factorial. We'll notice that cancels with that. So that gives us 56 is equal to, we'll multiply this out, so n squared minus n. We'll move 56 to the other side by subtracting it from both sides. So we've got 0 is equal to n squared minus n minus 56. Now we're going to utilize some of the math we learned in grade 11 and factor this. So we're going to be looking for two values that multiply to negative 56 and add to negative 1. So that would be negative 8 and positive 7. And then the values of n would be that make our equation equal 0 would be the ones that make each of these factors equal 0. So I've got positive 8 and negative 7. We'll do the same thing with this one. So we have 90 is equal to n times n minus 1 times n minus 2 factorial over n minus 2 factorial. Those cancel out. So we've got 90 is equal to n squared minus n. We'll move the 90 to the other side. So that gives us 0 is equal to n squared minus n minus 90. We'll look for two things that multiply to negative 90 and add to negative 1. So that'd be 0 is equal to n minus 10 and n plus 9. So that gives us n is equal to 10 and negative 9. Now with both these examples, we wrote out two answers, but with each one, only one is an acceptable answer because, like I mentioned, with factorial notation, we start with a number, keep subtracting till we get to 0. Now, if I plug 8 in for this n, where we've got n factorial, that's going to give us 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. So that works. But if I plug -7 in, that'd be -7 times -8 and so on. So it doesn't get to 0. So we can't actually have our, if we have n to factorial, it can't be a negative value. So that one wouldn't work and that one wouldn't work. So we've got n is 8 and then n is 10. Next example, write the following expressions using factorial notation. So some of these we'll be able to see what they are right away. Some we won't. So this one right here, we've got 6 times 5 times 4 times 3 times 2 times 1. So that's fairly straightforward. That's just going to be 6 factorial. Now this one is not quite that way. So it looks like we start out with 12 factorial. So that would be 12 times 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, but we're missing this part here. So that means we must have divided by 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, so that this canceled with this to leave us with this. So essentially that's going to give us 12 factorial divided by 8 factorial. Now, one thing to keep in mind is if we have factorial notation, we can't reduce these to lower terms. So we can't say that this is 3 factorial over 2 factorial. Okay, this next one looks like it's similar to this one, but we have this additional bit down here. So it looks like we have essentially 13 times 12 times 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. But we needed everything from 10 this way canceled off. So that would be dividing by 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. So that's essentially going to cancel out this part here with this part here. But that doesn't explain we still have a 3x times 2 times 1. So we need to account for that. So we still have times 3 times 2 times 1. So if we look at this top line is 13 factorial, while our denominator is 10 factorial times 3 factorial.